Before you drift any further, pause for just one quiet moment. What you're about to hear isn't speculation, and it isn't fantasy. It's how the universe actually behaves, confirmed by experiment, measured with care, and stranger than intuition allows. If calm, evidence-based science like this helps your mind slow down, tap the like button now. It quietly tells the algorithm this kind of learning deserves to exist. If you have a thought, a question, or even a quiet curiosity, leave a comment. I read every one, and they shape future stories. And if you'd like to fall asleep to real science again, subscribe so these journeys are waiting for you whenever the night feels long. You rest your attention on a world that feels steady and dependable. Objects fall, clocks tick, planets move along paths that can be predicted with care and patience. In this familiar picture, causes come before effects, and the future unfolds smoothly from the past. This is the landscape shaped by classical physics, a framework built slowly from observation, measurement, and mathematical description. You find comfort here because the rules feel intuitive. A thrown stone follows an arc. A pendulum swings with regular rhythm. Energy and motion behave in ways that align with everyday experience. For centuries, this view of nature offers extraordinary success. Bridges stand, cannons fire accurately, and navigation across oceans becomes reliable. The universe, at least at human scales, appears orderly, continuous, and deeply knowable through careful reasoning and experiment. It forms the quiet foundation upon which later questions gently begin to appear, without disturbance to daily understanding. You meet Isaac Newton's laws as clear statements linking force, mass, and acceleration. You learn how these ideas describe motion on Earth and in the heavens with the same equations. Gravity becomes a universal interaction, explaining falling apples and orbiting moons together. Later, classical electromagnetism expands this order. Electric and magnetic fields spread smoothly through space, carrying energy and information at a finite speed. Maxwell's equations unify light with electromagnetism, showing that waves can travel even through empty space. Everything seems continuous, deterministic, and precise. Given complete information, outcomes appear fixed in advance. This confidence is reinforced by success after success, from steam engines to telegraph cables. Nature feels like a vast clockwork, intricate but predictable, where uncertainty reflects only incomplete knowledge, not a limit built into reality itself. For a long time, this worldview satisfies both practical needs and deeper philosophical expectations about how nature should behave consistently always. Yet careful measurement slowly reveals details that resist this smooth picture. Atoms emit light only at specific colors, not in a continuous spread. Heated objects glow in patterns classical theory cannot predict accurately. When light strikes metal surfaces, electrons emerge in ways that depend on frequency, not intensity. These results are repeatable, precise, and unsettling. You see that experimental evidence, not philosophical comfort, guides scientific understanding. Small discrepancies accumulate, first as curiosities, then as persistent problems. Adjustments are tried, but the underlying assumptions remain strained. The classical tools that work so well for planets and engines begin to fail for the smallest constituents of matter. Nature seems to follow different rules at tiny scales, rules that do not smoothly connect with familiar expectations. The mismatch grows clearer as experiments probe shorter distances and higher energies with increasing precision, revealing limits that classical explanations can no longer comfortably hide from view. You remain grounded in the idea that science responds to observation. When predictions fail, theories must change. This principle leads to early quantum ideas, introduced cautiously to address specific problems. Energy appears in discrete packets during radiation and absorption. Mathematical descriptions adjust to fit measurements, even when intuition lags behind. These changes feel small at first, technical rather than revolutionary. Yet each correction weakens the assumption of continuity. Probability begins to enter descriptions of physical behavior. Instead of exact outcomes, ranges of possibilities become meaningful. You notice a shift from certainty to statistical expectation. The language of physics grows more abstract but also more accurate. What seems strange is not invented, but forced by data collected with care and repetition. In laboratories around the world, instruments quietly reveal patterns that theory must learn to respect, even when those patterns challenge long-held assumptions about physical reality shared by generations of scientists. You sense that something deeper is unfolding beneath these experimental facts. The small scale of atoms demands descriptions that differ from everyday experience. Classical paths and trajectories lose their clarity. Instead, measurable quantities are described by mathematical functions that encode likelihoods. This does not mean nature becomes arbitrary. The rules remain precise, but they govern probabilities rather than certainties. You learn that this approach predicts results with astonishing accuracy. The discomfort comes not from failure, but from success that contradicts expectation. As measurements grow more refined, the new framework proves unavoidable. The calm reliability of classical physics gives way to a subtler order, one that still obeys logic, but a different kind than intuition suggests. This transition unfolds gradually, guided by experiments that leave little room for alternative explanations built from consistent observations, rather than speculative reinterpretations of familiar ideas that once seemed entirely sufficient for describing natural behavior everywhere. You arrive at a quiet threshold where certainty softens without disappearing. Classical physics remains true within its domain, describing large objects and gentle motions with unmatched reliability. Yet at smaller scales, evidence insists on a different description. You do not abandon logic, you refine it. Cause and effect still operate, but through probabilities shaped by measurement. This shift does not diminish understanding. It deepens it. By accepting limits on what can be known simultaneously, predictions become more accurate, not less. The universe does not become unknowable. It becomes more precise in its demands. As your thoughts settle into this perspective, curiosity replaces resistance. The questions that emerge are not signs of failure, but invitations to learn how nature truly behaves when examined closely. These questions linger quietly, pointing toward relationships between measurements that stretch across space and challenge the assumption that physical systems are always fully independent from one another. You settle into a time when classical physics feels nearly complete, yet subtle problems persist. Measurements grow more precise, instruments more sensitive, and the smallest details of nature become visible. At these scales, light and matter behave in ways that resist smooth explanation. The calm confidence of 19th century physics begins to waver, not through dramatic failure, but through careful experiments that refuse to align with expectation. Each result is repeatable, methodical, and quietly persuasive. You notice that no single observation overturns the old framework. Instead, a pattern forms. The smallest pieces of nature seem to follow rules that are unfamiliar, but consistent. Scientists respond not with speculation, but with restraint, adjusting ideas only as far as evidence demands, allowing a new understanding to form slowly and carefully. One early puzzle appears in the study of heated objects. Classical theory predicts that an object should emit increasing energy at shorter wavelengths as temperature rises. Experiments show something different. Instead of an infinite rise, the energy peaks and then falls. This disagreement is not small. It is fundamental. Max Planck approaches the problem with mathematical caution. He proposes that energy exchange occurs in discrete amounts, later called quanta. This is not offered as a philosophical claim, but as a calculation that matches observation. Energy behaves as if it comes in packets, proportional to frequency. The idea feels strange, yet it works. What begins as a mathematical adjustment quietly reshapes how energy itself is understood at microscopic scales. Light soon presents its own challenge. Experiments show that shining light on certain metals ejects electrons, but only when the light exceeds a specific frequency. Increasing brightness alone does nothing. Albert Einstein explains this by extending Planck's idea. Light behaves as if it is made of particles, later called photons, each carrying a fixed amount of energy. Only photons above a threshold can free electrons. This explanation predicts results exactly. Light, once understood purely as a wave, now shows particle-like behavior under precise conditions. You notice that neither waves nor particles alone are sufficient descriptions. Instead, light responds according to how it is measured. This realization does not discard earlier knowledge, but refines it, guided by experimental consistency. Attention then turns inward toward atoms themselves. Classical physics predicts that orbiting electrons should radiate energy continuously and spiral into atomic nuclei. Atoms, however, are stable. Niels Bohr proposes that electrons occupy specific energy levels. They do not radiate energy while remaining in these states. Light is emitted or absorbed only when electrons transition between levels. This model explains atomic spectra with remarkable accuracy. Each element produces distinct lines, matching prediction and measurement. Though limited in scope, the model introduces an essential idea. Allowed states are discrete. Continuous motion gives way to permitted configurations. Stability emerges not from smooth change, but from restriction enforced by nature at very small scales. As these ideas accumulate, it becomes clear that a deeper framework is needed. Erwin Schrödinger introduces a mathematical equation describing how quantum states evolve over time. Instead of tracking precise positions, the equation governs a wave function. This function does not describe physical waves in space, but encodes probabilities for measurement outcomes. The square of its value gives the likelihood of finding a particle in a particular state. You notice a shift in language. Physics no longer predicts exact results, but distributions. This is not due to experimental weakness. The predictions are sharp, precise, and testable. Probability becomes an intrinsic feature of physical description, not a temporary stand-in for ignorance. At the same time, Werner Heisenberg develops a complementary approach focused on observable quantities. His formulation avoids picturing unmeasurable paths and instead connects measurable values directly. From this emerges the uncertainty principle. Certain pairs of properties, such as position and momentum, cannot both be known precisely at once. This is not a limitation of instruments, but a property of nature. Increasing precision in one quantity necessarily increases uncertainty in the other. You find that this principle is supported by experiment and embedded in the mathematics itself. The universe does not hide exact values beneath noise. Instead, it defines limits on what can be simultaneously known, with consistency and clarity. As quantum mechanics takes shape, debates arise about interpretation, but agreement forms around predictions. Every test confirms the theory's accuracy within its domain. Atoms behave exactly as described. Chemical bonds form according to quantum rules. Semiconductors, lasers, and magnetic materials all rely on these principles. You recognize that quantum mechanics is not abstract philosophy. It is a working theory, grounded in observation and engineering. Its strangeness lies not in vagueness, but in precision that defies everyday intuition. The equations do not describe uncertainty loosely. They define it mathematically, with outcomes verified again and again through experiment and application. You remain grounded in the understanding that classical physics still applies where it works. Large objects obey familiar rules because quantum effects average out. The new framework does not replace the old, but extends it. Quantum mechanics governs the small, while classical behavior emerges naturally at larger scales. This continuity offers reassurance. Nature is not fragmented, but layered. Different descriptions apply where they are appropriate. As your thoughts slow, you sense the calm logic beneath the unfamiliar form. The universe remains lawful, though its laws are more subtle than once imagined. In these quiet details, relationships between particles begin to appear that challenge the idea of complete independence, hinting that interactions may bind systems together more deeply than distance alone would suggest. You begin by letting go of the expectation that a physical system must always have a single, definite description. In classical physics, an object has a position, a velocity, and a path that exists whether or not anyone looks. In quantum physics, the description takes a different form. Instead of listing exact properties, a system is described by its quantum state. This state is not a vague concept. It is a precise mathematical object that contains all the information that can be known about the system. From it, every measurable prediction can be calculated. Nothing physical is missing from the description. What changes is the way knowledge itself is represented. You learn that a quantum state does not describe what a particle is doing in between measurements. Instead, it encodes the probabilities of different outcomes when a measurement is made. This does not mean the particle is unreal or undefined. It means nature limits what can be predicted with certainty. The quantum state reflects those limits exactly. When you measure position, the state gives a probability distribution for where the particle may be found. When you measure energy, the same state yields probabilities for specific energy values. Each prediction is precise, testable, and repeatable. The uncertainty lies not in the rules, but in the outcomes. The wave function is one common way of representing a quantum state. You may picture it as a mathematical function spread across space, but it is important to stay grounded in what it represents. It is not a physical wave like water or sound. It does not carry mass or energy through space in the usual sense. Instead, it assigns a numerical value to every possible configuration the system could take. When squared, this value gives the probability of observing that configuration. Experiments confirm this relationship with extraordinary accuracy. Wherever the wave function predicts a higher probability, measurements cluster accordingly. You notice that the quantum state evolves smoothly over time according to well-defined equations. This evolution is fully deterministic. Given the state at one moment, the equations specify the state at any later moment. The uncertainty does not grow from chaos or randomness in the equations. It appears only when a measurement is performed. At that point, one outcome is observed, chosen according to the probabilities encoded in the state. The theory does not explain why a particular outcome occurs, only how likely each outcome is. This limitation is not a flaw. It is a statement about how nature behaves at small scales, supported by consistent experimental evidence. Measurement plays a special role, but not a mysterious one. Measuring means allowing the system to interact with a device in a controlled way. That interaction produces a definite result. The quantum state connects directly to these results by predicting their frequencies over many trials. If the same measurement is repeated on identically prepared systems, the outcomes follow the predicted distribution exactly. You come to understand that the quantum state is not a statement about individual events. It is a statement about patterns. It tells you what will happen over time, across many measurements with remarkable reliability. You also learn that different measurements extract different information from the same state. A single quantum state can be used to predict many kinds of outcomes, but not all simultaneously. Measuring one property may change the state in a way that alters predictions for another property. This is not because measurement disturbs the system in a careless way. It is because the properties themselves are linked by the structure of the state. The mathematical relationships encode these limits precisely. The quantum state respects them automatically, without contradiction or ambiguity. As you grow more familiar with this description, you see that the quantum state replaces classical trajectories. There is no hidden path waiting to be revealed. Instead, the state represents all that can be known before observation. This idea has been tested through countless experiments. Interference patterns, atomic spectra, and particle collisions all behave exactly as predicted. The success of the quantum state lies in its restraint. It does not promise more certainty than nature allows. It provides exactly as much information as can be supported by observation, and no more. You begin to feel the quiet consistency beneath the unfamiliar language. The quantum state is not a guess or a metaphor. It is a working description that connects mathematics directly to experiment. Engineers use it to design devices that function reliably every day. Chemists use it to understand bonding and reaction rates. Physicists use it to predict outcomes with extraordinary precision. Its abstract form hides a deeply practical role. The calm order of nature remains, expressed now through probabilities rather than fixed paths. As your thoughts slow, you rest with the understanding that a quantum state describes a system completely, yet differently than classical intuition expects. It tells you not what will happen, but how often each possibility occurs. This shift does not weaken knowledge. It refines it. In this refined description, you begin to notice that when systems interact, their states may no longer remain independent, suggesting connections that extend beyond individual objects and into shared descriptions of physical reality. You remain with the idea of the quantum state, allowing it to settle gently into understanding. Within this description appears a feature that often sounds puzzling, yet follows directly from the mathematics and the evidence. This feature is superposition. In simple terms, superposition means that a quantum state can include multiple possible outcomes at the same time, each with a defined probability. This does not mean that a particle physically occupies many states in the everyday sense. It means the description of the system includes several possibilities simultaneously, weighted precisely by the rules of the theory. The calm clarity comes from remembering that superposition describes knowledge and prediction, not hidden activity beyond measurement. You see superposition most clearly in experiments with light and electrons. When particles pass through two narrow openings, the resulting pattern on a detector shows interference. This pattern cannot be explained if each particle travels through only one opening in a classical way. The observed distribution matches predictions made by adding probability amplitudes, not probabilities themselves. These amplitudes can reinforce or cancel each other mathematically, producing regions of high and low detection likelihood. Each particle arrives at a single point on the detector, yet over many trials the pattern emerges exactly as predicted. This behavior is not mysterious once the mathematical rule is accepted. It is simply how probabilities combine in quantum physics. You notice that superposition does not mean all outcomes occur at once in a physical sense. Instead, it means the quantum state includes multiple allowed outcomes before measurement. When a measurement is made, one outcome appears. Repeating the experiment many times reveals the full distribution. The theory does not claim that outcomes are unreal before measurement. It claims that only probabilities are defined before measurement. This distinction is subtle but important. It keeps the description grounded in observation rather than speculation. Superposition is a statement about prediction, not about hidden processes taking place beyond experimental access. You learn that superposition applies to many kinds of quantities. A particle can be in a superposition of positions, energies, or spin values. Each case follows the same rule. The quantum state assigns amplitudes to each possible result. The structure is consistent across experiments and systems. Nothing about this requires special interpretation or added assumptions. The mathematics is tested and confirmed. Superposition is not an extra feature layered on top of quantum mechanics. It is built into the way states are defined and how they evolve over time. As you stay with this idea, you find that discomfort often comes from imagining superposition in classical terms. Classical objects are always in one place, moving along one path. Quantum systems do not follow that description. They are not small versions of familiar objects. They are described by different rules because experiments show they behave differently. When classical intuition is set aside, superposition becomes a straightforward consequence of the theory. It does not suggest contradiction. It reflects the limits of classical language when applied beyond its domain of success. You also learn that superposition is fragile. When a quantum system interacts strongly with its surroundings, the delicate relationships between amplitudes are disrupted. This process, called decoherence, explains why superposition is difficult to observe in large objects. Interactions with air molecules, light, and thermal vibrations effectively erase interference patterns. This does not destroy quantum mechanics. It explains why classical behavior emerges naturally at large scales. Superposition remains present in principle, but its effects are spread out and become practically unobservable. This understanding connects quantum behavior smoothly to everyday experience. You see that superposition is not about uncertainty caused by ignorance. It is not that the system secretly has a definite state that is simply unknown. Experiments rule out such explanations in many cases. The interference patterns depend on the presence of multiple amplitudes, not hidden variables assigning single outcomes in advance. Superposition is therefore a feature of the description itself. It reflects how nature organizes possibilities at small scales, according to rules that are consistent and measurable. As your thoughts grow slower, you rest with the idea that superposition does not require mystery to be meaningful. It is a precise mathematical statement, confirmed by experiment and used in technology. Lasers, atomic clocks, and modern sensors rely on superposition to function. Engineers do not treat it as a puzzle, but as a reliable tool. The calm reliability of these devices mirrors the calm reliability of the theory behind them. Superposition works because it reflects how probabilities combine in the physical world. You remain aware that superposition becomes especially important when systems interact. When two quantum systems influence each other, their combined description may involve shared possibilities that cannot be separated cleanly. This quiet observation hints at a deeper structure within quantum mechanics, where the description of one system may become inseparable from another, even when they are no longer close together in space. You begin with a simple idea that feels familiar. When two objects interact, they influence one another. In classical physics, each object still keeps its own identity. You can describe one independently from the other, even while they exchange forces. In quantum physics, interaction leads to something quieter and more profound. When two particles interact, the most accurate description of reality may no longer belong to either particle alone. Instead, it belongs to the combined system they form together. This change does not arise from complexity or confusion. It follows directly from how quantum states are defined and how physical laws conserve measurable quantities during interaction. You rest with the understanding that every interaction must respect conservation laws. Energy, momentum, and angular momentum are not optional features of nature. They are observed invariants, confirmed in every experiment. When two particles interact, these quantities are shared between them in precise ways. In classical descriptions, this sharing can be tracked for each object separately. In quantum descriptions, the sharing becomes part of a single mathematical structure. The quantum state must account for the system as a whole, ensuring that conserved quantities are distributed consistently across all possible outcomes. This requirement alone is enough to link the particles together in their description. You notice how this works in simple examples. Two particles collide and then move apart. After the interaction, measurements of one particle's momentum are perfectly correlated with measurements of the other. If one is found moving in a certain direction with a certain speed, the other must compensate accordingly. This correlation is not added by hand. It appears automatically when the combined state is constructed correctly. The state describes all allowed outcomes together, not separately. The particles do not carry independent instructions. They share a joint description that reflects the constraints imposed by conservation laws and the interaction itself. You learn that this joint description is called a composite quantum state. It lives in a space that includes all possible combinations of outcomes for both particles. In many cases, this composite state cannot be written as two independent states multiplied together. When this happens, the system is said to be inseparable in its description. This inseparability does not imply that the particles are physically fused or permanently bound. It means that the most complete and accurate description treats them as parts of a single system, even if they later move far apart in space. You remain grounded in the idea that this is not an assumption. It is a consequence of how quantum states work. The mathematics is precise and unavoidable. Whenever particles interact and exchange conserved quantities, their states become linked. The strength and duration of the interaction determine how strong this linkage becomes. In some cases, the linkage fades as interactions with the environment overwhelm it. In others, it remains robust and measurable. The key point is that interaction creates shared structure in the quantum description, structure that cannot always be undone by separation in space alone. You find calm clarity in the fact that this does not require any special mechanism. There is no signal being sent after the interaction. There is no ongoing force holding the particles together. The shared description is established at the moment of interaction and remains valid as long as no further interactions disrupt it. The equations simply continue to evolve the combined state forward in time, preserving the correlations that were created. Measurement later reveals these correlations exactly as predicted. You also notice that this idea extends naturally to more complex systems. Atoms form when electrons and nuclei interact, creating shared states that define allowed energy levels. Molecules form when atoms interact, producing collective states that govern chemical behavior. Solids are built from countless particles whose combined states determine electrical and thermal properties. In each case, the most accurate description belongs to the whole system, not to isolated parts. Quantum mechanics scales naturally from the simple to the complex by repeating this principle again and again. You reflect on how different this is from classical expectation. In everyday experience, separation implies independence. In quantum descriptions, separation in space does not always restore separability in state. What matters is not distance alone, but whether interactions have linked the system in a way that persists. This idea feels subtle, but it is supported by countless experiments. Correlated measurements appear exactly where the theory predicts they should. Where interactions are weak or disrupted, the correlations fade. The rules are consistent and predictable. As your thoughts slow, you recognize that nothing here violates physical law. No conservation rule is broken. No information is created or destroyed improperly. The description simply acknowledges that some information belongs to the system as a whole. This shift does not complicate understanding. It refines it. By accepting that interaction creates shared descriptions, the behavior of quantum systems becomes clearer, not stranger. You rest with the quiet realization that once particles have interacted, asking for a complete description of each one separately may no longer be meaningful. The most accurate account may exist only at the level of the combined system. This gentle insight prepares the ground for understanding how deeply such shared descriptions can shape measurable outcomes, even when the parts involved are no longer close together in space. You remain with the idea that when particles interact, their most complete description may belong to the system as a whole. Within this understanding, a specific and carefully defined phenomenon emerges. This phenomenon is called quantum entanglement. Entanglement is not a vague connection or a mysterious influence. It is a precise statement about the structure of a quantum state. A system is entangled when its state cannot be written as a simple combination of independent states for each part. This definition is mathematical, exact, and directly tied to what can be measured. It does not depend on interpretation, imagination, or philosophy. It depends only on whether the predictions of the theory factor cleanly into separate pieces or not. You learn to distinguish entanglement from classical correlation. In classical systems, correlations arise when two objects share a common history or interact in predictable ways. For example, if two coins are placed in boxes after being arranged deliberately, their outcomes can be correlated without mystery. Each coin still has its own definite state, even if the observer does not know it. Quantum entanglement is different. There is no underlying set of definite properties for each part that merely remain hidden. Experiments demonstrate that no assignment of independent values can reproduce the observed statistical results. The correlation does not reflect missing information. It reflects a shared quantum state that contains information only about the system as a whole. You explore how this shared state is represented mathematically. In simple terms, the combined state includes terms that involve both particles together. These terms cannot be separated into products of individual states. When calculations are performed, predictions for measurements on one particle depend directly on the measurement context of the other. This dependence is not causal in the classical sense. It does not imply influence traveling between particles. It reflects the fact that the quantum state encodes joint probabilities, not independent ones. The structure of the state itself enforces these relationships with complete consistency. You see how this definition becomes operational through measurement. When measurements are performed on entangled systems, the results show correlations stronger than any allowed by classical theories that assume independent properties. These correlations appear across many trials, following exact statistical patterns predicted by quantum mechanics. No single measurement reveals entanglement on its own. Entanglement is revealed through patterns that emerge over time, through repetition and careful analysis. This requirement reinforces the idea that entanglement is not about individual events. It is about the structure of probability itself. You remain grounded in the fact that entanglement does not require proximity. Once established through interaction, the shared state evolves according to the same equations regardless of distance. The particles may move apart, but the mathematical description remains unified until further interactions alter it. This persistence is not added artificially. It follows directly from the rules governing quantum evolution. The equations do not include distance as a factor that weakens entanglement on its own. Only interaction with other systems can do that. This observation is confirmed by experiments in which entangled particles are separated by large distances while maintaining correlated outcomes. You learn that entanglement is not optional or rare. It arises naturally whenever quantum systems interact under suitable conditions. In practice, most interactions with the environment destroy observable entanglement quickly. This is why entanglement is not obvious in everyday experience. The environment acts as a vast measuring system, dispersing correlations into many degrees of freedom. Yet in controlled settings, entanglement can be created, preserved, and measured with precision. Laboratories around the world do this routinely, producing results that align exactly with theoretical predictions. You also learn that entanglement comes in degrees and varieties. Some states are weakly entangled, showing limited correlations. Others are maximally entangled, displaying the strongest correlations allowed by quantum mechanics. These distinctions are quantified using mathematical measures that compare predicted outcomes with classical limits. Such measures are not subjective. They are calculated directly from the state and verified experimentally. This allows scientists to treat entanglement as a resource, something that can be generated, manipulated, degraded, and restored under controlled conditions. You find reassurance in the fact that entanglement does not violate established physical principles. It does not allow faster-than-light communication. It does not break conservation laws. It does not undermine causality. The correlations it produces are subtle, revealed only when results from multiple measurements are compared. Each individual measurement outcome remains random. Only the joint statistics display structure. This balance preserves consistency with relativity while still allowing quantum mechanics to describe reality accurately. You rest with the understanding that entanglement is not an interpretation layered on top of quantum theory. It is a direct consequence of how states combine and how probabilities are calculated. Remove entanglement, and the theory no longer matches experimental data. Accept it, and predictions align with observation down to the finest detail. This acceptance requires no belief beyond what experiments demonstrate repeatedly. It requires only the willingness to let nature define its own rules. As your thoughts slow further, you recognize that entanglement reshapes what it means for systems to be separate. Independence becomes a property that must be demonstrated, not assumed. The quantum world allows wholes that are more informative than their parts. This insight does not disturb the calm structure of physics, completes it. In this shared structure, questions about measurement, correlation, and physical reality find a precise and testable expression, opening the way to deeper examination of how these correlations challenge long-held assumptions about locality and realism. You remain grounded in the growing success of quantum mechanics, yet you now encounter a calm and serious objection. Albert Einstein, along with Boris Podolsky and Nathan Rosen, does not dispute the accuracy of quantum predictions. Instead, the concern lies deeper at the level of description. A physical theory, in their view, should offer a complete account of reality. By complete, they mean that every element of physical reality should correspond to something in the theory. If a property can be predicted with certainty without disturbing the system, then that property should exist independently of measurement. This principle feels reasonable and familiar, rooted in centuries of classical thinking. The objection is not emotional or dismissive. It is careful, logical, and precise. You learn that another principle guides their thinking as well. This principle is locality. Locality holds that physical influences do not travel faster than light. Events occurring in one place should not instantly affect distant objects. This idea is not philosophical preference. It is supported by relativity and by every experiment involving signals and causation. Together, completeness and locality form a natural expectation about how the universe should behave. Einstein accepts that quantum mechanics works remarkably well, but he questions whether it tells the whole story or merely provides statistical rules for outcomes without describing underlying reality. To explore this concern, Einstein, Podolsky, and Rosen construct a thought experiment. They consider two particles that interact and then move far apart. Because of conservation laws, certain properties of these particles are correlated. Quantum mechanics describes this situation using a shared state. Measurements performed on one particle allow precise predictions about the outcome of corresponding measurements on the other, even when the particles are widely separated. According to the quantum description, these properties are not assigned definite values until measurement occurs. Yet the ability to predict with certainty suggests to Einstein and his colleagues that these properties must already exist. You pause with this reasoning. If you can predict the result of a measurement on a distant particle without interacting with it, then that result seems to reflect a real property of the particle. If that property is real, and if the measurement here does not influence the distant particle instantaneously, then the theory must already contain information about that property. Quantum mechanics, however, does not assign such definite values in advance. This leads to a tension. Either the theory is incomplete, missing underlying variables that determine outcomes, or it allows some form of non-local influence that violates locality. Einstein strongly prefers the first option. You notice that the argument does not claim quantum mechanics is wrong. It claims that it may be incomplete. The predictions remain correct, but the description may be missing deeper structure. This distinction matters. Many theories in physics have been incomplete yet useful, later replaced or extended by more comprehensive frameworks. The EPR argument, as it becomes known, is an invitation to search for a more detailed description that restores locality and realism while reproducing quantum predictions. You reflect on how carefully the argument is framed. It does not rely on hypothetical measurements that cannot be performed. It relies on logical implications of existing theory and well-defined experimental setups. It respects conservation laws and accepted principles. The calm strength of the argument lies in its restraint. It does not accuse quantum mechanics of contradiction. It highlights a choice that nature must make. Either accept non-local connections or accept that quantum mechanics does not fully describe reality. You learn that this challenge is not immediately resolved. Many physicists respond by questioning the assumptions behind the argument. Some suggest that the definition of completeness may be too strict. Others propose that locality may not apply in the same way at quantum scales. Still others explore the possibility of hidden variables, additional parameters that determine outcomes but remain inaccessible to direct measurement. These responses reflect healthy scientific debate. No consensus forms immediately. The discussion remains open, guided by logic and evidence rather than authority. You notice that what troubles Einstein most is not randomness. It is separation. The idea that a measurement performed here could define properties there feels incompatible with the structure of spacetime described by relativity. Even if no signal is sent, the coordination of outcomes appears unsettling. Einstein famously expresses this discomfort using vivid language, but beneath it lies a precise concern about how physical descriptions should respect causal structure. This concern motivates decades of careful thought and experiment. You remain aware that quantum mechanics continues to succeed during this period. Experiments confirm its predictions with increasing precision. Technologies based on quantum principles begin to emerge. Yet the conceptual tension remains unresolved. The EPR argument stands as a clear statement of what is at stake. It does not weaken quantum mechanics. It strengthens it by clarifying what must be tested. It turns philosophical discomfort into a scientific question that can, in principle, be answered by observation. You sense that the calm power of this challenge lies in its demand for clarity. Either nature respects locality in the classical sense, or it does not. Either properties exist independently of measurement, or they do not. These are not matters of taste. They are matters of how the universe behaves. The EPR argument insists that theory must answer these questions, not avoid them. As your thoughts slow, you rest with the realization that disagreement here is productive. By pressing on foundational assumptions, Einstein and his colleagues sharpen the questions that physics must confront. The universe is invited to respond through experiment rather than debate alone. In this quiet tension between prediction and principle, the stage is set for a way to let measurement decide which expectations about reality can be sustained and which must be gently released. You remain with the quiet tension left by the challenge to quantum mechanics, where logic alone is no longer enough. The disagreement centers not on predictions, but on explanation. To move forward, the questions must be reframed in a way that allows experiment to speak. This is where John Bell enters the story, not with interpretation, but with mathematics. Bell asks a careful question. If the world obeys locality and realism, what patterns of measurement outcomes are allowed? And if quantum mechanics is correct, what patterns should appear instead? His insight is to show that these two views do not merely differ in words. They differ in numbers that can be compared directly with experiment. You focus on the assumptions Bell makes explicit. Realism is the idea that physical properties have definite values before measurement. Locality is the idea that outcomes here are not influenced by choices made far away, faster than light could travel. Bell assumes both and asks what follows. He does not assume anything about quantum mechanics itself. He builds a framework in which hidden variables could exist, carrying predetermined instructions that determine outcomes. These variables may be unknown, but they are assumed to be local and independent. From these assumptions, Bell derives mathematical limits on how strongly measurement outcomes can be correlated. These limits take the form of inequalities. They specify the maximum correlation that any local realist theory can produce. The details are mathematical, but the meaning is clear. If experiments produce correlations stronger than these limits, then no theory based on local hidden variables can explain them. Importantly, Bell's inequalities are not abstract. They refer directly to measurable quantities. They involve counting how often certain combinations of outcomes occur when measurements are performed under controlled conditions. This makes the question empirical. Nature will either respect these limits or exceed them. You learn how the experimental setup works in principle. Two particles are prepared in a shared quantum state and then separated. Each particle travels to a distant location where one of several possible measurements can be chosen. The choices are made independently. For each run, outcomes are recorded. After many repetitions, the correlations between outcomes are calculated. Bell's inequalities specify how strong those correlations can be if locality and realism both hold. Quantum mechanics, using entangled states, predicts correlations that exceed those limits under specific measurement choices. You notice something subtle and important. The predicted violations do not appear in every situation. They require carefully chosen measurements and states. This means the test is not trivial. It must be designed with precision. This requirement strengthens the result rather than weakening it. If violations appear exactly where quantum mechanics predicts and nowhere else, the conclusion becomes difficult to avoid. The theory is not being stretched to fit data. It is being tested under conditions it specifies in advance. You remain aware that Bell's theorem does not say quantum mechanics is complete or incomplete. It says something more precise. It says that no theory based on local hidden variables can reproduce all the predictions of quantum mechanics. If experiments agree with quantum predictions, then at least one of the assumptions behind Bell's inequalities must be abandoned. Either realism, locality, or both must be reconsidered. Bell does not tell you which to give up. He shows that keeping both is incompatible with observed correlations. You take comfort in the clarity of this result. The debate is no longer philosophical. It is framed in terms of frequencies, probabilities, and statistical limits. The inequalities provide a clean boundary between classes of theories. They do not depend on interpretation. Any theory that respects the assumptions must obey them. Any violation points beyond that class. This is the strength of Bell's work. It translates deep questions into testable predictions without adding speculative elements. You also learn that Bell's inequalities apply broadly. They do not depend on the details of a particular hidden variable model. They apply to all models that share the same basic assumptions. This universality makes the result powerful. It rules out an entire category of explanations at once, rather than addressing them one by one. If violations are observed, they cannot be patched by adjusting details. The assumptions themselves must be revised. You remain grounded in the role of probability. Bell's theorem does not claim that individual outcomes are predetermined or random. It concerns patterns across many trials. The inequalities constrain averages, not single events. This aligns naturally with how quantum mechanics makes predictions. Individual outcomes remain unpredictable, but the statistical structure is precise. Bell's inequalities test that structure against classical expectations in a way that respects how experiments are actually performed. You consider the role of measurement choice. For the test to be meaningful, the choice of which measurement to perform on each particle must be independent and unpredictable. If the particles somehow knew in advance which measurements would be chosen, they could coordinate outcomes in a classical way. Bell's framework accounts for this by requiring independence between hidden variables and measurement settings. This requirement is not arbitrary. It reflects the physical idea that choices made here should not be constrained by distant events in the past in a conspiratorial way. Experiments are designed to satisfy this condition as carefully as possible. You also learn that Bell's theorem respects relativity. It does not assume or require faster-than-light signals. It tests whether correlations can be explained without such signals. The violations predicted by quantum mechanics do not involve communication. Each outcome remains locally random. The correlations appear only when results are compared later. This distinction preserves causality while still challenging classical intuitions about independence. You find reassurance in the fact that Bell himself approaches the problem with humility. He does not claim to know what reality ultimately is. He shows what it cannot be if certain experimental results are observed. This negative result is still profound. It narrows the space of possible explanations. It forces clarity about assumptions that might otherwise remain implicit and unexamined. As your thoughts slow, you sense the calm power of this moment. A question once debated in words is now framed in numbers. The universe is invited to answer, not through interpretation, but through measurement. Whatever the outcome, understanding will deepen. Either classical expectations will be reinforced in an unexpected way, or quantum mechanics will reveal something fundamental about how separation and correlation coexist in nature. In this quiet readiness for experiment, the abstract tension between locality and realism prepares to meet the steady clarity of observed data. You remain with the readiness to let nature answer for itself. Theoretical arguments have narrowed the possibilities, but only careful experiment can decide which expectations about reality hold. Physicists take up this task with patience and precision. The goal is simple in statement and demanding in practice. Measure correlations between distant particles under conditions that satisfy the assumptions behind Bell's inequalities. Every detail matters. Timing, distance, detector efficiency, and randomness of measurement choices must all be controlled. What follows is not a single experiment, but a sequence of increasingly refined tests, each addressing potential weaknesses of the last. You begin with early laboratory tests using pairs of photons produced together and sent in opposite directions. These photons carry correlated properties such as polarization. At each side, a detector measures polarization along a chosen orientation. Over many runs, the outcomes are compared. The statistical correlations exceed the limits set by Bell's inequalities, aligning instead with quantum mechanical predictions. These results are striking, but physicists remain cautious. They examine whether hidden assumptions could still explain the data. This careful skepticism strengthens the process rather than weakening it. One concern involves detection efficiency. Early experiments fail to detect every particle produced. If undetected particles behave differently from detected ones, correlations could appear artificially strong. This possibility is known as the detection loophole. To address it, Researchers improve detectors and use systems where detection rates are high enough that missing events cannot explain the results. As technology advances, experiments close this loophole step by step. The correlations persist, unchanged in their strength and pattern. Another concern involves timing and communication. If measurement settings on one side could influence outcomes on the other through ordinary signals, even very fast ones, classical explanations might survive. To prevent this, experiments ensure that measurement choices and outcomes occur within time windows too short for light to travel between detectors. Random number generators select measurement settings at the last possible moment. This closes the locality loophole. Again, the correlations remain exactly where quantum theory predicts. You notice how these refinements are not rushed. Each improvement is tested repeatedly. Data is collected over long periods. Statistical analysis is performed with transparency and rigor. Independent groups reproduce the results using different particles, different distances, and different methods. Experiments are performed with photons, electrons, and atoms. In each case, the same pattern appears. Bell's inequalities are violated under conditions where no classical local explanation remains viable. You remain aware that no single experiment stands alone. Confidence emerges from convergence. When multiple approaches yield consistent results, doubt narrows. By the early 21st century, experiments simultaneously close major loopholes within the same setup. These tests meet the strictest standards envisioned by Bell himself. They show, beyond reasonable doubt, that nature does not obey local realism in the classical sense. The universe behaves in accordance with quantum mechanics, not because of philosophical preference, but because measurements say so. You find calm clarity in what these experiments do and do not show. They do not demonstrate faster than light signals. They do not show that outcomes are controlled remotely. Each measurement remains locally random. The correlations appear only when results are compared afterward. No usable information travels instantaneously. Relativity remains intact. What changes is the assumption that physical properties exist independently and locally in a way that fully determines outcomes. The data does not support that view. You also see how restraint remains central. Physicists do not claim that experiments reveal the ultimate nature of reality. They claim something more modest and more powerful. Certain classes of explanations are ruled out. Any theory that assumes both locality and pre-existing independent properties cannot reproduce the observed correlations. This is a clear boundary set by experiment. What lies beyond that boundary is open to interpretation, but the boundary itself is firm. You rest with the understanding that this resolution is not dramatic. There is no sudden collapse of intuition. Instead, there is quiet adjustment. The universe has answered a specific question. It has shown which expectations must be revised. The calm strength of science lies in accepting this answer without embellishment. The results stand on their own, supported by data, replication, and consistency. As your thoughts slow further, you sense how these experiments reshape the landscape of understanding. They do not end inquiry. They focus it. By settling what cannot be true, they open space to explore what remains possible. In this measured clarity, attention turns naturally toward how such correlations can exist without violating causality, and how quantum mechanics maintains internal consistency while allowing connections that reach beyond classical separation. You remain with the experimentally confirmed reality of quantum entanglement, and now your attention turns toward clearing away ideas that do not belong. Entanglement is often described in ways that extend far beyond what evidence supports. These descriptions may sound compelling, but they add confusion rather than understanding. To rest comfortably with the science, it is important to see clearly what entanglement does not do. By removing false expectations, the genuine structure of the phenomenon becomes calmer and easier to hold in mind. You begin with one of the most persistent misunderstandings. Entanglement does not allow information to travel faster than light. Even though measurements on entangled particles are correlated, no message can be sent using those correlations alone. Each measurement outcome is fundamentally random. You cannot choose the result you obtain. Because of this randomness, there is no way to encode a signal. Only when results from both sides are later compared do the correlations become visible. This comparison requires ordinary communication at or below the speed of light. Relativity remains fully respected. Every experiment confirms this limitation without exception. You notice how this follows directly from probability. Suppose two distant observers measure entangled particles. Each observer sees a random sequence of outcomes. Without access to the other side's data, nothing unusual appears. There is no pattern that can be controlled or interpreted as a message. The correlations emerge only in joint analysis. This is why entanglement cannot be used for instantaneous communication, no matter how sophisticated the setup. The theory itself prevents it, and experiments confirm the prevention every time. You also learn that entanglement does not involve any signal being sent at the moment of measurement. There is no physical influence traveling between particles when one is measured. The correlations do not arise dynamically at that moment. They are already encoded in the shared quantum state established earlier through interaction. Measurement reveals what the state already predicts. Nothing propagates across space. Nothing is transmitted. This distinction is subtle, but essential for maintaining consistency with known physical laws. Another misconception you gently release is the idea that entanglement allows one particle to control another. Control requires choice. Entanglement offers no such control. You cannot decide the outcome of a measurement on one particle, and therefore you cannot decide the correlated outcome elsewhere. Both results remain unpredictable individually. The connection lies in statistical structure, not in influence or command. This makes entanglement fundamentally different from any classical mechanism of control or communication. You also set aside the idea that entanglement implies particles are somehow aware of one another. Awareness implies internal states with goals or responses. Quantum particles show no evidence of such features. They follow mathematical rules that predict probabilities, not intentions. Entanglement does not require particles to know anything about each other. It requires only that their joint description includes correlations enforced by conservation laws and quantum structure. The language of awareness adds nothing to understanding and has no experimental support. You rest with the realization that entanglement does not imply hidden coordination occurring after separation. Once particles interact and become entangled, the shared description evolves according to fixed equations. Nothing further needs to happen. There is no ongoing process maintaining the correlation. The persistence of correlation is not an active effort. It is a passive consequence of how the state was prepared and how it evolves. This quiet persistence often feels strange only because everyday experience suggests that separation ends connection. Quantum mechanics shows that this expectation does not always apply at small scales. You also clarify that entanglement does not contradict causality. Causes still precede effects within any given frame. Measurements performed here do not alter past events elsewhere. The correlations do not allow paradoxes or causal loops. They appear only when data is brought together afterward. This structure preserves the logical order of events. Time retains its direction. The universe does not become inconsistent. The calm reliability of causal structure remains intact throughout all confirmed experiments involving entanglement. Another idea you let dissolve is the belief that entanglement explains consciousness or perception. There is no evidence linking quantum entanglement to mental processes in a way that goes beyond ordinary physics. While quantum effects are essential at atomic scales, biological systems operate in environments where decoherence dominates. The fragile correlations required for entanglement do not survive long in warm, complex systems. Claims that entanglement underlies thought or awareness remain speculative and unsupported by experiment. Science requires evidence, and here the evidence does not point in that direction. You also learn that entanglement does not blur the distinction between observer and system in a mystical way. Measurement involves physical interaction, not observation in a psychological sense. Detectors register outcomes through well-understood processes involving amplification and decoherence. Human awareness enters only at the level of reading results. Entanglement does not require consciousness to function. It operates the same way whether or not a human is involved in the experiment. This reinforces the objectivity of the phenomenon. You remain aware that entanglement does not make all particles everywhere connected. Entanglement is specific. It arises through interaction and is limited by subsequent interactions. Most particles in the universe are not entangled with one another in any observable way. Environmental interactions rapidly destroy entanglement. The phenomenon must be carefully created and protected to be studied. This specificity keeps entanglement grounded and prevents it from becoming a vague universal explanation for unrelated effects. You also let go of the idea that entanglement removes individuality entirely. While the joint description matters, individual measurements still yield individual outcomes. Each particle is detected at a definite place with a definite result. The shared state does not erase individuality. It reshapes how probabilities relate across systems. This distinction helps preserve clarity between what is shared and what remains local. You notice how many misunderstandings arise from stretching language beyond its proper domain. Words like connection, influence, and link carry everyday meanings that do not map cleanly onto quantum descriptions. When these words are used carelessly, confusion follows. When the mathematics and experiments are allowed to speak directly, the picture becomes simpler. Entanglement is neither magical nor paradoxical. It is precise, limited, and consistent. You rest with the understanding that removing false ideas does not diminish wonder. It refines it. The real phenomenon is subtle enough without added speculation. The fact that nature allows correlations stronger than classical expectations, while still preserving causality and relativity, is already remarkable. No embellishment is needed. The calm structure of quantum mechanics stands on its own, supported by measurement and consistency. As your thoughts settle, you find that clarity brings ease. Knowing what entanglement does not do allows you to focus on what it does accomplish within physics. It becomes a well-defined feature rather than a source of confusion. In this calm understanding, attention naturally shifts toward how entanglement operates quietly within ordinary matter and physical systems, shaping behavior at small scales without announcing itself loudly in everyday experience. You turn your attention away from carefully isolated laboratory setups and toward the wider physical world. Entanglement is often discussed as something rare or delicate, created only under special conditions. Yet when you look closely, you find that entanglement is woven into the fabric of ordinary matter. It does not announce itself dramatically. It operates quietly, shaping the behavior of systems at atomic and subatomic scales. The reason it feels unfamiliar is not because it is absent, but because its effects are usually hidden beneath layers of interaction that smooth out its most striking features. You begin with atoms, the simplest stable structures built from interacting particles. An atom is not a collection of independent objects moving separately. The electrons and nucleus are described together by a shared quantum state. The allowed energy levels of an atom arise from this combined description. Electrons do not belong to specific orbits in a classical sense. Their properties are defined only in relation to the whole atomic system. This inseparability reflects entanglement between electrons and the nucleus, enforced by electromagnetic interaction and conservation laws. Without this shared structure, atoms would not exhibit the stable spectra observed so precisely in experiments. You extend this understanding to molecules. When atoms bind together, their electrons form collective states that span multiple nuclei. Chemical bonds are not tiny mechanical hooks. They are manifestations of shared quantum states. The electrons involved are entangled across the molecule, producing energy configurations that lower the system's total energy. These configurations determine molecular shape, strength, and reactivity. Every chemical reaction relies on the rearrangement of these shared states. Entanglement here is not optional. It is essential for chemistry to function as it does. You move further outward to solids. In metals, electrons are not confined to individual atoms. They occupy collective states extending across large numbers of atoms. These shared states explain electrical conductivity, thermal behavior, and magnetic properties. In superconductors, Entanglement plays a central role in allowing electrons to move without resistance. The behavior appears macroscopic, yet it originates from quantum correlations established at microscopic scales. The remarkable properties of these materials arise not despite entanglement, but because of it. You notice that entanglement is also present in light itself. Photons produced in certain processes naturally emerge in correlated states. These correlations appear in atomic emission, particle interactions, and even in astrophysical environments. While most naturally occurring entanglement is quickly disrupted by interaction with surrounding matter and radiation, its brief presence still influences how energy and information are distributed. The universe does not need human intervention to create entanglement. It arises whenever quantum systems interact under the right conditions. You then reflect on why entanglement is rarely observed directly outside laboratories. The reason lies in the environment. Every system is surrounded by countless others. Air molecules, thermal radiation, vibrations, and electromagnetic fields interact continuously with matter. These interactions cause decoherence, a process that spreads quantum correlations into many degrees of freedom. As a result, the distinctive signatures of entanglement become inaccessible. The system still obeys quantum laws, but its behavior averages out into patterns well described by classical physics. This transition does not eliminate entanglement in principle. It makes it practically unobservable. You find calm reassurance in how natural this process is. Decoherence does not represent a failure of quantum mechanics. It explains why the world appears classical at large scales. The same rules apply everywhere. Only the balance of interaction differs. Where interactions are controlled and minimized, entanglement can be preserved and measured. Where interactions are abundant and uncontrolled, entanglement disperses. This continuity connects laboratory experiments smoothly with everyday experience. You also learn that entanglement plays a role in nuclear physics. Inside atomic nuclei, protons and neutrons are bound together by strong interactions. Their collective behavior cannot be described as independent particles. Shared quantum states determine nuclear stability, decay rates, and reaction pathways. These effects govern processes from radioactive decay to energy production in stars. Entanglement here operates under extreme conditions, yet remains subject to the same principles tested in smaller systems. You turn your thoughts to the larger universe. In the early moments after the universe began expanding, matter and radiation interacted intensely. Quantum correlations formed naturally during this period. While most of these correlations were quickly lost through interaction and expansion, their influence shaped the distribution of energy and matter. Subtle imprints of early quantum processes appear in patterns measured today, such as fluctuations in cosmic radiation. These observations do not require speculative interpretation. They arise from well-established physical models tested through observation. You remain careful not to overextend the idea. Entanglement does not remain intact across cosmic distances in any simple way. Interactions with intervening matter and radiation break correlations rapidly. The universe is not a single entangled system in any observable sense. Entanglement is local in its creation and fragile in its persistence. Recognizing these limits keeps understanding grounded and precise. You also notice how entanglement influences measurement devices themselves. Modern sensors, atomic clocks, and interferometers rely on carefully managed quantum correlations to improve precision. These technologies work not by amplifying entanglement indefinitely, but by controlling it briefly and purposefully. This practical use reinforces that entanglement is not an abstract curiosity. It is a measurable resource with predictable behavior when handled carefully. You rest with the realization that entanglement is part of the quiet infrastructure of reality. It shapes how matter holds together, how energy moves, and how systems respond to interaction. Its effects are usually subtle, masked by complexity and interaction, yet always present beneath the surface. Understanding this does not make the world feel less familiar. It makes it feel more deeply connected at fundamental levels. As your thoughts grow slower, you sense how entanglement bridges the microscopic and the macroscopic without disrupting either. It allows small-scale quantum rules to give rise naturally to stable large-scale structures. In this calm continuity, attention gently turns toward how physicists learn to harness entanglement deliberately, treating it not just as a background feature of nature, but as a practical tool shaped by careful design and control. You turn your attention to how entanglement moves from quiet background feature to practical tool. In nature, entanglement often appears fleetingly and disappears quickly under environmental interaction. In technology, physicists and engineers work deliberately against this tendency. They do not attempt to preserve entanglement indefinitely. Instead, they create it when needed, protect it just long enough, and use it for specific tasks. This approach reflects a deep understanding of the phenomenon's limits as well as its strengths. Entanglement becomes useful not because it is mysterious, but because its behavior is predictable under controlled conditions. You begin with quantum communication. One of the clearest technological uses of entanglement appears in secure information exchange. When two distant systems share entangled particles, measurements performed on those particles show correlations that cannot be reproduced by classical means. These correlations allow the detection of any unwanted interference. If an outside party attempts to extract information from the system, the correlations change in measurable ways. This principle underlies quantum key distribution. The security does not come from secrecy of method, but from physical law. Any disturbance leaves evidence. This makes security a property of nature rather than computation. You notice that entanglement does not transmit the message itself. Ordinary communication channels are still required. Entanglement is used to verify integrity, not to carry content faster or farther than light allows. This distinction preserves causality while enabling new forms of trust. The system works because entanglement constrains what correlations are possible. When observed correlations match predictions, participants gain confidence that the channel has not been compromised. This calm reliance on physical law replaces assumptions with measurement. You then explore quantum computing. Here, entanglement allows certain problems to be approached differently than in classical machines. Quantum bits, or qubits, can share states that encode information collectively. This collective encoding allows operations to act on many possibilities at once within a single computation. Entanglement ties qubits together so that the state of one cannot be described independently of the others. When carefully controlled, this structure allows algorithms to extract global properties of data more efficiently than classical approaches. You remain grounded in realism. Quantum computers do not try every answer simultaneously in a literal sense. They manipulate probability amplitudes through interference, amplifying correct outcomes and suppressing incorrect ones. Entanglement is essential for this process because it allows correlations between qubits to shape these amplitudes collectively. Without entanglement, quantum computers lose their advantage and behave much like classical systems. This dependence highlights that entanglement is not an optional feature. It is central to how these machines operate. You also learn why building such devices is difficult. Entanglement is fragile. Interactions with the environment cause decoherence, disrupting the shared state. Heat, electromagnetic noise, and material imperfections all contribute. Engineers respond by isolating systems, cooling them to extremely low temperatures, and correcting errors actively. These efforts are not attempts to fight nature blindly. They are precise responses to well-understood physical processes. The challenges arise from scale and complexity, not from lack of understanding. You move next to quantum sensing and measurement. Entanglement allows measurements to reach sensitivities beyond classical limits. By correlating particles in specific ways, noise can be reduced and signals enhanced. Atomic clocks use entangled states to improve timekeeping accuracy. Interferometers use entanglement to detect extremely small changes in distance or field strength. These improvements do not violate uncertainty principles. They redistribute uncertainty in ways that favor the quantity being measured. The result is greater precision within the same physical limits. You notice how this use of entanglement remains subtle. It does not produce dramatic effects visible to the eye. It sharpens measurements quietly. The improvements are incremental but profound. Over time, They enable technologies that rely on extreme precision, such as navigation systems, gravitational wave detection, and tests of fundamental physics. Entanglement here acts as a quiet refinement rather than a radical transformation. You also see how entanglement supports simulation of complex quantum systems. Certain physical systems are too intricate for classical computation to model accurately. Quantum simulators use entangled particles to mimic the behavior of these systems directly. By observing how the simulator behaves, scientists gain insight into materials, reactions, and phases of matter that would otherwise remain inaccessible. This approach does not replace theory. It complements it by offering a new experimental window into complex quantum behavior. You remain aware that these technologies do not depend on speculative interpretations. They rely only on the operational rules of quantum mechanics that have been tested repeatedly. Engineers do not debate whether entanglement is real. They measure it, quantify it, and manage it. This practical stance reflects confidence built on decades of experiment. The phenomenon works consistently enough to support design, testing, and deployment. You also understand why entanglement is always used locally and temporarily. Attempts to scale entanglement across large systems face exponential difficulty. Noise grows, control weakens, and correlations degrade. Rather than pushing against these limits blindly, technology adapts. Systems are modular. Entanglement is created where needed and released when its role is complete. This strategy mirrors how nature itself uses entanglement briefly during interaction before allowing it to disperse. You rest with the realization that entanglement becomes powerful precisely because it is constrained. Its limitations define its usefulness. It enhances specific tasks without overturning established physical principles. It respects causality, thermodynamics, and relativity. Its value lies in precision, not excess. This balance keeps quantum technology grounded and realistic. As your thoughts slow, you sense how entanglement moves smoothly from abstract concept to working tool. It does not demand new beliefs about reality. It demands careful design, patience, and respect for physical limits. In this quiet partnership between theory and engineering, attention naturally turns toward how these technologies deepen understanding itself, using entanglement not only to build devices, but to test the boundaries of knowledge with ever greater subtlety. You arrive at a place of quiet adjustment rather than resolution. The discoveries surrounding quantum mechanics and entanglement do not demand that you abandon everyday experience. They ask only that you recognize its limits. At human scales, the world behaves as it always has. Objects move predictably, causes precede effects, and separations imply independence. These patterns remain reliable because quantum effects average out through constant interaction with the environment. Classical reality is not an illusion. It is an emergent description that works where it is meant to work. The deeper rules do not replace it. They support it from beneath. You begin to see that living with a non-classical reality does not mean constantly confronting strangeness. It means accepting that intuition is shaped by scale. The brain evolves to navigate a warm, noisy environment filled with large objects. It is not tuned to predict the behavior of isolated particles. When experiments reveal behavior that feels unfamiliar, the discomfort arises not from inconsistency, but from mismatch between intuition and evidence. Science resolves this mismatch by trusting measurement over expectation. This trust has guided progress repeatedly, from the motion of planets to the structure of atoms. You notice how quantum mechanics exemplifies this process. It does not ask you to believe in invisible forces or hidden intentions. It asks you to accept statistical descriptions where certainty is unavailable. The theory does not promise answers to questions that nature does not permit. Instead, it provides exact rules for predicting outcomes where prediction is possible. This restraint is one of its strengths. Over decades of testing, quantum mechanics has produced no internal contradictions and no verified failures within its domain. Its predictions align with observation to extraordinary precision. You reflect on how this reliability shapes daily life quietly. Modern electronics rely on quantum behavior in semiconductors. Medical imaging depends on quantum interactions between radiation and matter. Navigation systems depend on atomic clocks whose accuracy emerges from quantum structure. None of these technologies require philosophical interpretation to function. They require only that the rules work. Their success confirms that quantum mechanics describes something real, even if that reality does not align with classical imagery. You also see how accepting non-classical structure does not undermine meaning or stability. The universe remains governed by laws. These laws are consistent, discoverable, and shared. They do not change with perspective or belief. The fact that some outcomes are probabilistic does not mean the universe is arbitrary. It means the rules operate at a level where distributions matter more than individual events. This shift preserves order while redefining certainty. Over many repetitions, patterns emerge with unwavering regularity. You become aware that non-classical reality does not erase objectivity. Measurements remain public and repeatable. Experiments performed in different places by different people yield the same results when conditions match. The role of measurement does not elevate observers to a special status. It reflects physical interaction between systems. Detectors respond to particles whether or not a human is watching. Consciousness does not shape outcomes. The universe behaves as it does regardless of attention. You find calm in how boundaries are respected. Quantum mechanics does not allow unlimited connection. Entanglement does not dissolve distance into irrelevance. Causality remains intact. Energy remains conserved. Information remains constrained. The theory stretches intuition without breaking coherence. Where connections appear stronger than classical expectations, they do so within strict limits enforced by mathematics and experiment. These limits preserve consistency with relativity and thermodynamics, ensuring that non-classical does not mean chaotic. You reflect on how this understanding changes how questions are asked. Instead of demanding certainty where none is available, science learns to ask what can be known and with what reliability. Instead of insisting on separability as a default assumption, it examines when separability applies and when it does not. This flexibility does not weaken inquiry. It sharpens it. By aligning questions with what nature allows, understanding deepens rather than fragments. You also notice that living with non-classical reality encourages humility. The universe does not arrange itself to match expectation. It reveals itself gradually through careful observation. Each time intuition fails, knowledge expands. This pattern repeats throughout scientific history. Quantum mechanics is one of its clearest examples. The theory survives not because it feels comfortable, but because it survives tests. In this survival lies its authority. You rest with the idea that mystery remains, but not in the sense of ignorance. Mystery exists at the boundary of what can be asked meaningfully. Quantum mechanics does not explain why the rules are what they are. It shows how they operate. This distinction keeps inquiry open without undermining what is already known. Future theories may extend understanding further, but they will need to reproduce quantum mechanics where it has been tested. Progress builds forward, not backward. You sense how this perspective settles into daily thought quietly. The world feels no less solid. Objects still rest where placed. Time still flows forward. Yet beneath these experiences lies a deeper structure that does not need to be visualized to be real. Accepting this layered reality allows both familiarity and depth to coexist. The surface remains calm while the foundation remains rich. As your thoughts slow, you find ease in letting reality be what observation shows it to be. Certainty gives way to consistency. Intuition gives way to evidence. The universe remains understandable, though not always predictable in detail. In this calm acceptance, curiosity softens rather than sharpens, becoming a quiet companion rather than a demand for resolution, allowing understanding to rest gently within the limits nature itself has set.